Welcome to qnawire.
Hi, so over here we're going to have the following phase diagram for SO2, in which we want to answer the following questions. So first of all, we need to identify the phases on our phase diagram. This is going to be the solid, the liquid, and the gas phase respectively. So what is going to be the normal melting point that is going to be going from solid to liquid at 1 atmosphere? This is going to correspond to the temperature over here. This is going to be the melting point. So the temperature corresponds to 200.4 Kelvin. The normal boiling point is going to correspond to, at 1 atmosphere, the transition in between liquid and gas, so this is going to be equal to 263.1 Kelvin. At 1 temperature and pressure, do the three phases coexist at equilibrium? This is going to be our triple point, and is going to have the value for temperature of 197.6 Kelvin and a pressure of 0.0017 atmospheres. Next up, is sulfur dioxide a solid, a liquid, or a gas at room temperature and pressure? At room temperature, we're going to be at around 273 Kelvin, all the way probably to 293, maybe 300, depending. And as you can see, at a pressure of 1 atmosphere, this is going to be a gas. Which one is going to be the more dense phase, the liquid or the solid? In this case, we have a positive slope on the solid liquid intersection, so that means that the solid is going to be more dense. And finally, we're going to have a 27.1 gram sample of liquid sulfur dioxide that is going to be heated at constant pressure from 263.1 Kelvin to 346.1 Kelvin. So in this case, the change of temperature would correspond to 346.1 minus 263.1, both of them in Kelvin. So the change would be equal to 83 Kelvin. And the transformations that we're going to have are starting from liquid at the boiling point, the heat that is going to be required would correspond to the mass times the enthalpy of vaporization plus the mass times the heat capacity of the gas phase times the delta T for the gas. Notice that we are starting at the boiling point, so that means that we need to transform all of the liquid into gas. So the values that are provided over here are that the delta H of vaporization is going to be equal to 389 joules per gram, and the specific heat for the gas phase is going to be equal to 0.623 joules per gram Kelvin. So the heat required for this process is going to be 27.1 grams times delta H of vaporization, which was 389 joules per gram, plus the mass, 27.1 grams, times the heat capacity of the gas, 0.623 joule per gram Kelvin, times the delta T for the gas, which is 83 Kelvin. So with this, the value of the heat is going to be 11,943.2 joules, which converted to kilojoules is going to be equal to 11.943.2 kilojoules. And with that, it will be all. Thank you very much and have a good one.